My name is Ms. Camarillo. We're going to be doing the vectors section today for Math 2412 for the Math Happy Hour. So let's get started. So we got a lot to cover. These are some of the objectives, and those of you taking the class, these are coming from section 6.3 and 6.4 of your book. We're going to look at vectors, component form of a vector, magnitude. We're going to look at vector operations, unit vectors, linear combinations of vectors, direction, angle, look at some word problems, and then finish off with the dot product, an angle between two vectors, orthogonal vectors, and a projection of vector u onto v. So let's go ahead and get started. So what is a vector? An introduction to vectors. So quantities such as force and velocity involve both a magnitude and direction and cannot be completely characterized by a single number. So to represent such a quantity, we use a directed line segment. So we have an example right here. Directed line segment, so directed has a direction and you indicate that with an arrow. So we start here, you have an initial point, you start at P. And usually where we end, we call it Q. And again, you know the initial point because it's not where the arrow is. The terminal point is the one with the arrow. And because it goes from the P to Q, we call this vector PQ. So this is an example right here. So like I was explaining, initial point P, terminal point Q. So some of the things we talk about for a vector are its magnitude or its length. And that's denoted by what looks like double bars of an absolute value on the outside. So we have double bars on the outside. When we have that around a vector, that means to find its length, or we'll call that the magnitude. So how do we do that? How do we find the length? Well, you've actually done it before when you found the distance between 2 points. So that's the distance formula. So looking at it again, some more terminology. Here's a vector. Another name for the initial part is the tail. It ends at the head. The direction that it's going, that's important with the arrow. And you see the magnitude here is this length. But like I was mentioning before, you've used the distance formula. That is the distance between 2 points. We can use that as well here to find the magnitude or the length of a vector. Okay, so two directed line segments, when they have the same magnitude and the same direction, they are going to be equivalent vectors. So we have some examples here. All of these vectors are the same length and they're all pointing in the same direction, so they will be equivalent. Okay, they're in different spots, so they have different beginning and ending points, but they will be equivalent. So the set of all directed line segments that are equivalent to another line segment, PQ, is a vector V in the plane. So we have, for example, this vector V is the PQ. So we can also denote vectors by lowercase bold letters. U, V, and W are common. So when you see lowercase bold letters, it's usually a vector. You will also see these lowercase letters with a little arrow on top to indicate that they are vectors, okay? Again, if they are equivalent, their lengths or magnitudes are the same, and the direction or their slopes are going to be the same. Okay, so again, for magnitude, we're going to use the distance formula. Okay, and we have for the direction, we use the slope. So you guys should know your slope formula, the slope between 2 points. So again, here's our distance formula for magnitude, distance between 2 points. You would plug in the coordinates x and y of each of the points. And as a reminder, here's your slope formula. Okay, you have 2 points and we plug in the x and y values to find the slope. So that's where we're going to start. Our example is, how do we show that two vectors are equivalent? So I have two vectors here, u and v. U goes from P to Q. This is vector v from R to S. So how do we show that they are equivalent? Well, we have to find their length or their magnitude, and we have to find the slope. If they are the same for both vectors, then the vectors are equivalent. So again, we have the distance formula for the magnitude and we have the slope formula. So we're going to use that to plug everything in. Okay, so let's start with the first vector u. Our initial point P is 0, 0. Our terminal point or ending point is Q, 3, 2. So that's our vector u, which is also, again, PQ. So let's look at the values that we have for x and y. Again, P 0, 0, so x1, y1 is 0, 0. Q is 3, 2, but we're going to label that as our second point. So x2 is 3, y2 is 2. So putting it this way helps you see what you're plugging into the formulas. So starting with the distance formula, let's plug everything in. It's x2 minus x1 squared plus y2 minus y1 squared. So I'm plugging in those values. So x2 minus x1, 3 minus 0. Y2 minus my y1 is 2 minus 0. So we plug everything in and simplify. 3 minus 0 is 3. 2 minus 0 is 2. We got to square them. We're going to get 9 plus 4, which is 13, square root of 13. So the length for that one, or the magnitude, is square root of 13. We also have to find the slope, so let's do that. So we have change in y over change in x. And again, the way we wrote out the points, it looks easy to plug everything in, all the values in. So y2 minus y1, 2 minus 0, all over x2 minus x1, 3 minus 0. That simplifies to 2 over 3. So the slope of this vector is 2/3. So now we have to do the same thing for our other vector. We have to find the distance and the slope, or the magnitude and the slope and the direction. If it's the same, then we know that the vectors are equivalent. So we're going to do the same thing, but now these are our points. This is the vector v right here, or rs. R is coordinates 1, 2. S is coordinates 4, 4. So when we write out the points, the first point, x1, y1 is 1, 2. Our next point, S, x2 and y2 are 4 and 4. So that's going to help us plug everything in appropriately. We're going to start with finding the magnitude, or again, the distance. Plugging in the values appropriately right here, x2 minus x1 squared plus y2 minus y1 squared. So I plug in the appropriate values, 4 minus 1 squared, 4 minus 2 squared, gives me with 3 squared and 2 squared, leaves me with 9 plus 4, and I get the square root of 13. I also have to find slope for this one, so I'm going to plug values in appropriately into the equation. So the slope is going to be change in y, so 4 minus 2, all over the difference in the x's, 4 minus 1. We get 2/3. So what do you notice? Because they have the same magnitudes, or the same distance here, square root of 13, and looking at the slopes, they have the same slope values, 2/3 for both. That's how we know that these vectors are equivalent. If they maybe had the same length but not the same slope, or maybe the same slope but not the same distance, then they wouldn't be equivalent. These both have to match. But since they do, these two vectors are equivalent. Okay, now we're going to talk about the component form of a vector. The component form of a vector, you start with initial point P and terminal point Q is given by here. We're going to take the difference of the coordinates Q1 minus P1 and Q2 minus P2. Q2 minus P2, and that's the component form. So we're using initial point. We're looking at that as P1, P2 instead of what we normally see, X1, X2. And our terminal point is Q. We're calling that Q1, Q2 for the coordinates instead of X2 and Y2. So let's look at an example. So I have a vector right here, initial point -1, -5, ending point -3, 1. So if I want to write that in component form, okay, again, I'm rewriting this formula right here. I'm going to go ahead and subtract Q1 minus P1 and Q2 minus P2. So I have the values right here. I'm going to appropriately plug them in. So Q1, -3 minus P1 minus -1, and Q2 minus P2, 1 minus -5. Change the signs here. I'm going to end up with -3 plus 1, which is -2, and 1 plus 5, which is 6. Okay, so it's important to know what that means. So here's the original vector, right? When you write it in component form, that means that if we moved this vector to the origin, it would end up at these coordinates, -2, 6. So again, component form is like moving a vector right? Let's see this vector, right? If I take this vector where it was and I just slide it over to start at the origin instead of initial point wherever it is, it's like we're moving it to the origin, and then component form is giving us what that terminal point would be, again, if I just move that vector to the origin. So that would be -2, 6, okay? So looking at it graphically, that's what it is to write a vector using its component form, okay? In addition, we're looking at what is the magnitude or length of this vector. So again, if you look at it as it's a vector that started at the origin 0, 0, instead of having to subtract, we know that the initial points are 0, 0 in component form. We could just square these two components in component form. So here's our original formula. Well, we can use this formula if you want to subtract the coordinates, but once it's in component form, to find the magnitude or the length, we can just square each of these components, square root of that, okay? Another thing to keep in mind, we're going to look at when the length or the magnitude of vector is 1, that's called a unit vector, okay? Also, if the length or magnitude of vector is 0, that's only when v is the 0 vector, okay? So keep those definitions in mind as well, okay? So here are the formulas again. We started with distance formula, but then we replace x and y with p and q. And then you can also look at that as just once a vector is in its component form, you can just square the two components in that vector. All of those are the same for finding the magnitude of a vector. Okay, so let's do another example. We're going to find the component form and the magnitude of this vector. It's giving us the initial point and the terminal point. So let's rewrite it. We have the initial point 4, -7. That's our P, so P1 and P2. We have our terminal point, -1, 5. That's our Q, so we're going to label these Q1 and Q2. That's going to help us plug it into the formula to rewrite it in component form. Remember, we subtract. We do Q1 minus P1 and Q2 minus P2. That's going to give us our vector in component form. Okay, so let's split up our values here. P1 is 4, P2 is -7, Q1 is -1, and Q2 is 5 to see it better and then plug it into the equation, our formula better. So Q1 minus P1, -1 minus 4, Q2 minus P2, 5 minus -7, that double negative becomes plus. So -1 minus 4 is -5, and 5 plus 7 is 12. So this is the component form for our vector. Next was to find the magnitude. Okay, so we have this formula, but again, it's the same as just squaring now each component for that vector, right? So here it is in component form again. Again, we can just square each part. So we can take -5 squared, 12 squared, take the square root of all of that instead of having to subtract, right, both of the points that we have, right? So if I just plug in -5 and 12 into the formula, I'm going to get square root of 25 plus 144, gives me square root of 169, and the square root of that is 13. So the magnitude of this vector in component form was 13. So again, once we know how to write a vector in component form, okay, you got to subtract, you have the initial point and the terminal point. Finding the magnitude is a little bit easier because now you just have to plug in these numbers right here. Square each number and take the square root of all that, and we have our magnitude, okay, which again is the length of that vector. Okay, let's do another example. Find the component form and the magnitude of this vector. Initial point of 17, -5, and terminal point of 9, 3. Okay, so to split that up to see that better, remember the initial point is our P. So we have P1 and P2. Our terminal point is Q, so we're going to have Q1 and Q2, and we can label those just to help us see that and plug that into our formula better. Again, here's the formula for writing a vector in component form. Appropriately plugging in the values, 9 minus 17, 3 double negative, 3 minus a -5. 9 minus 17 is -8, and 3 plus 5 gives us 8. So this is the component form for this vector. It also wants the magnitude. So again, once you have it in this form, we're just going to square each part here and take the square root of all that. So we have negative 8, and 8 was the original vector that values we're going to plug in. So it's negative 8 squared plus 8 squared, 64 plus 64. I want the square root of all of that. I get square root of 128, which simplifies to 8 square root of 2. So just to briefly go over this, how did I simplify this, right? In the previous example, it was a perfect square, so we got a whole number. This one, when you want to try to simplify a root, you're looking at factors of this number that are perfect squares. 64 is a factor of 128, and that's important because I know 64 is a perfect square. So I'm going to rewrite 128 as 64 times 2, and it's all under the square root because it's square root of 128. So square root of 64 times square root of 2. Again, I chose these factors because there's other factors of 128, but I chose these because square root of 64 is a perfect square. Square root of 64 is 8. So that's where I get the 8 and the square root of 2. So keep that in mind. If you need to review, come see the tutoring centers so we can look at how to simplify a root. Okay, but that would have been the answer right there for the magnitude. Okay, so let's look at another cool way of looking at finding the component form of a vector. Okay, so going back, here's our formula for the component form for the vector. You have your initial point, P1, P2, terminal point, Q1, Q2. Now look at this cool observation. If we take the values of the Q, the points for Q, Q1, Q2, and we just subtract the values of the P, or change the signs of the coordinates of P, we can just go ahead and do that, and we get that formula, right? Q1 minus P1, Q2 minus P2. So it's another way to set it up and another way to do that for finding the component form of a vector. So let's see what this looks like as an example if we set it up this other way. Again, you take the Q, 0.93, you subtract the P or change the signs of the P vector, or of the P point. So we have 9,3. If I change the signs, I have a negative 17 and a 5, or we take the opposite of that, right? So 9,3, change signs, negative 17, 5. And now what? We just add these up. 9 and negative 17 is negative 8. 3 and 5 is 8. So this is a cool observation, the way it works out. It's a cool way to set it up to find the component form of a vector. Take your Q, change the signs of the P or the initial point, and then go ahead and do the operation and add them up right there. Okay. So again, terminal point minus initial point, or terminal point, change the signs of the initial point, add them up to get the vector. Okay, so another example here, we're going to do it using the form we did on the previous slide, using our observation, which is, again, you take the terminal point, you switch signs of the initial point, and you just add up appropriately the coordinates, right? So I have a negative 8, negative 9 is my terminal point. I'm going to change the signs of my initial point. So it becomes negative 1, negative 3, and now I'm going to add up. So add the first coordinates together. Negative 8, negative 1 is negative 9, and negative 9, negative 3 is negative 12. So that's a pretty cool way to do that and find the component form of the vector. Next, it wants the magnitude. So again, once you have the vector in component form, we're just going to take the square root of squaring the first term and the second term. So there's our formula, plugging in appropriately. So we have the negative 9 and negative 12 that we plug in here. Square them, 81 plus 144 inside the square root. That adds up to 225, square root of 225, and this is a perfect square, so the square root of 225 is 15. Magnitude is 15. Okay, so now we're going to go on to looking at some vector operations. We're going to first start with looking at sum and a scalar multiple. So we have a u and a v vector right here, so u will be u1, u2, v is v1, v2. And let k be a scalar, just a number, right? So here are the definitions. When you want to add two vectors, You're going to add the first components of each one, so you have u1 plus v1 get added, and then you're going to add u2 and v2 together, okay? When you're going to multiply a number, a scalar, it's called a scalar multiple. K is some real number. When you want to take a number times a vector, you're just going to multiply that number times both parts of the vector, right? So K times U1 and that K number, whatever it is, times the U2. So we're going to look at some examples using this, okay? As well as, what if you want the negative of a vector? Well, you just multiply everything by the negative. That scalar would be a -1. So both parts get multiplied by that -1, and you take the opposite, right, of each of those parts of the vector. When you want to take the difference of u and v, you're going to subtract two vectors. It would be the same as just adding the opposite or adding the negative of that second vector. So we can go back and use our addition rules once we just change the signs or take the negative of that second vector, the vector that's being subtracted, and now we can look at it as just adding. Okay. Here's the formula for the difference of, you want to look at it. So once we're subtracting, you would just subtract the first parts of the vectors, u1 minus v1 and u2 minus v2. Okay, so let's look at some examples. If I have this vector -2, 5 component form, vector w, 3, 4 in component form, let's do some operations with that. So let's start with A here. We have 2v, which is 2 times the vector v, okay? So 2 times v, so that means 2, the scalar, times this vector, -2, 5. So what do we do from, if you recall, we're going to take 2 times each of these parts of the vector. So 2 times the -2 is -4. 2 times 5 is 10. So that's how we get 2 times v. Not bad, okay? So you just multiply the number in front, or multiply the number times each part, each component of that vector. Okay, -4, 10 for that one. Here it is graphically, so you can see that and know what it means. On some of them, you have to pick the graph that represents the operation. So here we started with the original component vector, -2, 5. So again, like I mentioned before, component vector means that if we start at the initial point 0, 0, this would be our terminal point. So if I was at 0, 0, the vector -2, 5, terminal point would be here. That's my vector v. So from 0, 0 to -2, 5, okay? So when I do 2 times that, right, I'm doubling this value. So I just take this vector right here, and I'm going to double it. So I put it, start another vector at the end of this one and go up again, and I just doubled that vector. So that total length is what we got by multiplying, -4 and 10. So now it ends at -4, 10 once I did the doubling, or times the 2. Okay, so another way to think about that too is you have the original vector -2, 5, and if we go again, how we from here, let's say this is our new starting point, but I want to double it, so I'm going to go -2, 5 again, right? So we can note that graphically from here, going -2 to the left, because the first component would represent how we move left or right. And then I'm going to go 5 up, because the second part tells me how I move up or down. So that's a +5. So now I'm going to go up 5. And I end up from here, if I go 2 units to the left, 5 units up, I end up at -4, 10. So that's one way to see this operation graphically. Okay, let's look at, it's not letting me go to the next slide. Sorry guys, I got stuck. Let me see. Let's see if I can do it like this. Oh, sorry, I have other slides. I'm not, let's see, how do I get to slide 13?
Maybe you can refresh the browser and then go back to slide 12.
Okay, I exited, so let me see. Okay, I was done with slide 12. Let me see if it lets me start on slide 13. Sorry, I'm sorry, I don't know what happened today. Okay, so that one should be done. Let's see if I can start on, are you guys still seeing my screen?
Yes, it's just slow on loading.
Yeah, I don't know what happened today. I'm so sorry. But
Are
I
you
am
able
here
to
on slide
close
13.
maybe some other things you have open? Maybe it'll help free up some memory.
Okay, well, it's just my, there we go. Okay, here's slide 13. I'm going to try to do it in presenter mode. Yeah, because this doesn't have the animations. Presenter view. Okay, let's see. Oh, and it just went
We
to
see
slide.
it. We see it. And then now just to your slide.
Let's see if it takes me to 13, guys. Down here. Let's see. Nope. Okay, well, it goes through all the animations.
If you go to the right, you can click on that slide view and then pick the slide. So down where the arrows were.
Yeah, I was trying to, but it doesn't let me. I'm clicking on the bottom.
The what box with a bunch of boxes inside?
Yeah, I don't know if you see it on my, but I have down here, it shows me the slide, like I'm on slide 9 of 31.
Right. The slide view
I'm
is
trying.
the one right next to the arrow to the right. That one right there. See all
Oh,
slides?
I see
And
what
then
you're
pick
saying.
slide 13
Okay.
and it should go. Yes. Okay.
Oh, but that's not 13. This is the one we already did. Let me try it again, guys. I'm sorry. Okay, I'm picking slide 13. It's not taking me there. This is the
I'm sorry.
slide we already did. And you know what? And I'm stuck here. It doesn't let me. I'm so sorry. I don't know why it doesn't go beyond. Let me pick 14. Nope. This is the last slide we did, guys. Wow.
What would you like to try to do?
Let me see. I can still go through it. There's no animations, but so everything's on the screen. Let me try one more time opening it. This is how I usually do it, is I open it in the desktop.
Okay. Yeah, we can definitely try it.
But this is the issue I was having, and I was, before we logged in, it wasn't opening the PowerPoint in the desktop view.
I suppose if you want, we can just stay on the screen you're on and,
Okay.
and try to go through it
Yeah.
that way.
Yeah. Okay. Yeah. So, sorry, I don't know what I've been doing it the same every week. I don't know what happened differently this time, guys. I'm so sorry.
Hey, Melinda, you want me to finish it for you?
I mean, I have, it's up to you. I mean, I have it here, right? You guys see it. I don't know why it's not letting me.
No,
It's up to you, Alberto.
If you want, yeah, if you want, I can finish it. That way it'll be complete. Yeah, so let me
Okay.
let me share my screen, and that way I can continue on slide 13. Is that okay with you, Melinda?
Okay, yeah. So well, it might be a little different because I do add or I change. So you're just looking for, whatever example I was on. You know what? Let me try. Let me see if this is gonna load. It'll tell me like, hey, it might have worked. Oh no, see, it's not opening. Yeah, it tells me it's not. Okay, yeah, I don't know, Alberto, if you want to.
No, but I'll do it then. Okay, I'll do it. That's okay.
Let me see what I need to do. Do I need to stop sharing?
I think stop
Yeah,
sharing.
you just click the stop sign. The stop button at the top corner. Right there. Yeah. There you go.
Okay, so let's see. Mystery Sassy will take over where I left off.
Okay, let me share my screen then.
Thank you. Sorry.
Let's see, slide. Can you guys see my screen, right?
Yes, sir.
Yes, sir.
I believe we said over here. Okay, so let me start from here.
Yeah, that's the right one. Like I told you, I do changes, so the sides might not match. But yeah, there you go.
Okay, guys, I'm going to continue here with, after Ms. Camarillo with example 3. I think we're going to continue on part B, I think, W minus V. Okay, so, the W vector is component 3, and 4, minus the V vector, will be negative 2, 5. Okay, again, so this turns to addition, right? And then we switch the signs on the second vector, which is vector V. And now we do is just add them. So it's going to give us 5, -1. Okay. Now, again, here's the observation again. Right, I'm going to put the W vector, which is 3, 4, then minus vector V. Right, so then I'm going to continue here, and I'm going to change the signs on vector V. Right, and I would do as add them, vertically. So it's going to give us 5, -1. Because this is crucial, guys, because you're going to see it again when you take calculus 3. There's a whole chapter on vectors, which is chapter 11. And when I teach that class, I like to show them these observations because it's easier for them to get the vector, the component form, and also the magnitude. Okay, so the answer was 5, -1, correct? Well, here's where it starts. We start with vector W, right, which is this one here, right, which will be from the origin all the way to 3, 4. This vector W. And then, right, here we follow the slope, right? So, the slope is like y over x. That's why it's going to go down 5 from the point 3, 4. And then, right, it's rise over run. So then I'm going to go to the right too. And then we connect this vector here from 3, 4 all the way to 5, -1. And then this will be my answer. Here in bold, right? So this answer, will be my W plus -V. Okay, that's how you, sketch them. And then, as Mario said earlier, you're gonna have to pick, I think, multiple choice on your web assign, homework. Let's do another one. Let's do a C, V plus 2W. So it's gonna be -2, 5, right? Because that's vector V, and plus 2 times vector W. First, we're going to multiply the scalar 2 times vector W times 3 and times 4, right? Which will give us 6 and 8. Now we're going to add them. It'll be -2 plus 6 and 5 plus 8. So it's going to give us 4, 13. And again, here's the observation. Right, it's going to be vector V plus 2 times vector W. So there's my vector V. And here's my 2 times vector W. Right, it's going to give us 6, 8 on the bottom, on the bottom vector, which is vector 2W, and we add them vertically. So it'll be 4, 13. Now, how does the graph go? Right, again, we're going to start at vector V, right? So this is vector V from 0, from the origin to the point -2, 5. Then we're going to go up 8, right? Because again, this is like my x and my y, right? On a plane, and the slope is rise over run. So we're going to go up 8 from the point -2, 5, and we're going to go across 6, right, to the right, because both are positive. It's going to go up and to the right, and then we will match the point -2, 5, right? This vector with the one here, guys, which will be 4, 13. So the vector in bold is a 1 that's V plus 2W. That's how you sketch them. Now comes unit vectors. Unit vectors means that the length or the distance is 1, or the magnitude, same thing is 1. Okay, so this is my formula. It's going to be the vector over its magnitude. Or you can rewrite it as 1 over the magnitude of the vector V times the vector itself, which is vector V. Example, find a unit vector U in the direction of V. And vector V is equal to -2, 5. Those are my components. And then you have to verify that the unit, the vector U, right, is a unit vector by the magnitude is equal to 1. Okay? So what do we need to do? I need to find, because we're already given the vector itself, right, vector V. So I need to find the magnitude, right? This is vector V with component -2 and 5. So we put it on the distance formula, right, which would be -2 squared plus 5 squared, and we take the square root of that, which will give us the square root of 29, right? Now I got the vector, and I got the magnitude, right? So it's going to be the vector itself, which is -2, 5, over the magnitude, right? Then we can separate them. It's going to give us, because this vector, the same thing as 1 over the square root of 29 times vector -2, 5, which will give us -2 over the square root of 29 and 5 over the square root of 29. Now we're going to place these two components inside the distance formula, right? Which is the magnitude. Now, if we square the negative 2 over the square root of 29, is going to give us 4 over 29. If we square the 5 over the square root of 29, is going to give us 25 over 29. When we add them, it's going to give us the square root of 29 over the square root, the square root of 29 over 29, which will give us 1. That's how we verify that the unit, this is 1 unit, right? Because it's equal to 1. You see? Find a unit vector u in the direction of v. V is equal to a component 6, comma, component 1. And then we have to verify that it's a unit vector. Okay, it's going to be the same thing as what we did earlier, but just a different vector. Again, we need to find the magnitude, which would be the square root of 6 squared plus negative 1 squared. So it's going to give us the square root of 37. Right, now we plug into the formula. So it's going to be the vector v, which is component 6, negative 1, over the square root of 37. Now it's going to give us 6 over the square root of 37 and negative 1 over the square root of 37. Now we're going to use the magnitude formula or the distance formula, right? We're going to place both components, the v1 component and the v2, put it inside the square root. So it will give us the square root of 6 over the square root of 37 squared plus negative 1 over the square root of 37 squared, which will give us 36 over 37 plus 1 over 37, which results in the square root of 37 over 37, which is equal to 1. That's how you verify it. Now, this is another form to write a vector, right? We learned how to do it in component form. Now, this is called the linear combination form of a vector. I believe when you do physics and when you do calculus 3, we don't use a component form anymore. They like to use the linear combination form, which is I stands for the v1 component and j stands for the v2 component. For example, right? This is my j vector, right? Because it's like my y, and this is my I vector, which is like my x. Okay, now component form, right? Say they give you vector v is equal to a component negative 5, 12. So to write it as linear combination, it's going to be vector v is equal to negative 5i plus 12j. And a common mistake that students make is that they want to put those or the symbol, right, for the vector for component form. They want to put it here too, guys, and it's wrong. It's either you write it in component form or you write it in linear combination form. You cannot have both of them there. And a lot of students, that's what they do. Okay, so again, this is called component form, and this is called linear combination form with the I and the j. Okay, now writing a linear combination of a unit vectors. So again, here, guys, they're going to give you 2 points. This is my initial point, which is 2, negative 5, and my terminal point is negative 1, 3. They want you to write. They want you to name this vector as vector u. They want you to write it as linear combination of the standard unit vectors I and j. Okay. So again, I'm going to go straight to the observation. So it's going to give us a terminal point, which is negative 1, 3, point Q. And point P will give us, if it's minus, right, we're going to switch the signs on the initial vector, the initial point, which is 2, 5. So it's going to be negative 2 plus positive 5. All we do is add them, and it becomes a vector. Negative 1 minus 2 will give us negative 3, and 3 plus 5 will give us 8. So this is my unit. This is the vector in component form, correct? But they want it as linear combination form. So what we do is, right, this is component form. So the negative 3 becomes negative 3i, and the 8, positive 8, becomes plus 8j. So again, this is component form, and on the bottom is a linear combination form. Again, vector operations, but now they don't have them in component form anymore, right? They have them as linear combination form. So we apply the same concept as before. Here, right? They give us vector u is equal to negative 3i plus 8j, and vector v is equal to 2i minus j. They want us to find 2 times vector u minus 3 times vector v. Solution: it is not necessary to convert u and v to component form to solve this problem. Just perform the operation with the vectors in unit vector form. Okay. So again, guys, right? So the 2 times vector u is the same thing as 2 times negative 3i plus 8j minus 3 times vector v, which was 2i minus j. So we distribute the scalar. So 2 times negative 3i will give us negative 6i. And 2 times positive 8j will give us 16j. Right? And then negative 3 times 2i will give us negative 6i. And negative 3 times negative j will give us positive 3j. So here we're going to add the combined like terms. We're going to add the i's and the j's. So negative 6i. I think there's a mistake here. Let me see here. Because we got, 6i minus 6j will give us 6i minus 6i will give us negative 12i. And 16j plus 3j will give us the 19j. Okay, now, we can do it this way also, guys, right? It's better to put them vertically because, vertically, the i's and the j's are vertically aligned, and the addition or subtraction will be easier. So first we start with vector 2 times vector u, which will be 2 times negative 3i plus 8j. If we distribute the scalar, it's going to give us negative 6i plus 16j. Then the minus 3v, right? Negative 3 times vector v will give us negative 3 times vector v, which was 2i minus j. Again, we distribute the scalar, the negative 3. Negative 3 times 2i will give us negative 6i. And negative 3 times negative j will give us a positive 3j. You see, and they're aligned vertically for an easy, it's more, it's easier to do. Negative 6i minus 6i will give us negative 12i. And 16j plus 3j will give us the 19j. Okay? And again, guys, like I tell my students that it's easier to do it vertically. Okay? Because it's easier to do. And there's a less of a chance for you to make a mistake. Now comes finding direction angles of vectors. Here, for example 8, we have two parts. A, find the direction angle of the vector. Hey guys, the most important thing here, guys, is you have to know what quadrant is the vector on. Okay? Right, because the direction angle is determined by the tangent of theta is equal to b over a. Right? So my b is like the y part, right, on the coordinate plane, and the a is like my x part. Okay? So here's what you got to know. In your calculator, you can put theta is equal to the arctangent or the inverse tangent of b over a. So if it's in quadrant 1, right, the answer in the calculator, that'll be the answer. Whatever you get. If it's in quadrant 2 or 3, you're going to have to add 180 degrees or pi. It depends if they want it in degrees or if they want it in radian. Right, so again, quadrants 2 and 3, and right now I'm going to explain why. And then if it's quadrant 4, most of the times they want the answer as a positive answer. So you have to add 360 degrees or 2 pi. And here's the reason why, guys. Remember when we did the inverse? And I believe the range for the arctangent or the inverse tangent is from negative pi over 2 to pi over 2, which is quadrant 1 or quadrant 4. So the answer, will always be in quadrant 1 or 4. For example, if it's in quadrant 1, right, both the x and the y are positive. So if you put it into the calculator, guys, it's going to give you that answer. But what happens if it's in quadrant 3? In quadrant 3, the both x and y, they're both negative. And you write, if you divide negative divided by a negative, it's going to give you a positive. But the calculator, only gave you quadrants 1 and 4. So to go from quadrant 1 to quadrant 3, we have to add pi. That's the reason why, guys, if it's in quadrant 1, that's your answer. Quadrants 2 and 3, you add 180 degrees or pi. And quadrant 4, because it wants the answer as a positive angle, you add 360. Just remember these when you're doing finding the direction angle of a vector. So now, for part A, right? What's a quadrant? If you notice, they're both positive. So it's going to be positive what quadrant 1 because both are positive, the x value and the y value. So here, guys, the answer that we put in the calculator, guys, that's going to be the answer. Okay. So it's going to be the tangent of theta is equal to 3 over 3. So the arctangent of theta is equal to 1, right? But this one doesn't really need, the calculator, because you guys should be aware that anything with a 4 in the bottom, right, from the unit circle is going to be 1. But it depends on the quadrant. For example, on quadrant 1, it's going to be pi over 4 or 45 degrees. Okay, and you plug it into the calculator, it will give you 45 degrees if you have the mode in degrees, or they will give you 1/4 pi, which is the same thing as pi over 4 if you have it in, the mode in radians. So that's my answer. Now let's repeat the process for for B part, right? And here's my sketch, right? Quadrant 1, and that's the angle that we're looking for, which is 45 degrees. Now for B part, again, we follow the same procedure as before, as part A, right? So B part, guys, if you notice, it's positive negative, which means it's going to be in quadrant 4, right? Which means I have to add 360 degrees because I want the answer as a positive angle. But if you put it into the calculator, it's going to give you a negative, negative angle, going on the opposite, direction as a unit circle, right? Because the positive goes up, like counterclockwise, and the negative goes down counterclockwise. So that's why, guys, we have to add 360 because we want the answer as a positive angle. But let me show you what I'm talking about. Okay, we will need to add 360 to theta because it's in quadrant 4. So this is going to give us, right, the arctangent of negative 4 over 3. So it will be negative 53.13010.235 degrees. If you notice, this is in quadrant 4, right? Again, because if you have the unit circle, right? If you're going clockwise, right, it's going to be negative. That's why we have to add 360, which is a coterminal angle, and make it positive. So this will be equivalent to 306.87 degrees. So these 2 points actually are the same on the unit circle. But since this is not one of those perfect, what they call the perfect triangles, like the 45, 45, 90 and the 30, 60, 90, right? That's why, these points are actually not because, not there because they're not those 2 perfect or those 2 special triangles. But anyway, guys, what you have to remember here is that if it's in quadrant 1, right, it's going to be the answer is what it is. If it's in quadrants 2 or 3, you can add 180 degrees or pi. And if it's in quadrant 4, if you want the answer in positive, you have to add 360 or add 2 pi. That's what you have to remember, for doing these type of problems. Okay, and here's my sketch. Okay, for example, hey guys, this angle here, right, going towards the negative side, it's going to be negative 53.13010.235, right? But since you want the positive one, we add 360. So if we add 360 all the way around, it's going to give us this angle here, which will be 306.87 degrees. Okay. Now finding the velocity vector. It says find the component form of a vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 30 degrees below the horizon, below the horizontal, as shown in the figure 6.21. Okay, that's my figure. So here's the formula that we need to know. Okay, but first of all, right, they're saying that the magnitude is 100, right, which is the length, or the magnitude is 100 miles. And theta is 210, right? This is 210 here. So here's a formula, right? For the, for this type of problem, the vector is equal to its magnitude times cosine of theta I plus the magnitude of sine of theta j. Here, right? The 100 is my magnitude. So we have to know the components of 210, right? What's the point? There's an x and a y value. So in 210, right, which is the same thing as 7 pi over 6. The cosine or the x value is negative square root of 3 over 2. and the y value is also negative 1/2. So it's going to be 100, right? For the cosine, we're going to plug in the x value, which is negative the square root of 3 over 2 I, and then for the sine of 2tan, we're going to this is equal to negative 1/2. So then this becomes negative 50 the square root of 3i minus 50j. Okay, now how can we make sure that this is 100? Okay, by finding this, the magnitude. So the magnitude of the vector that we just found, right? The square root of negative 50 squared of 3 squared minus negative 50 squared. If you notice, it's going to give me 7,500 plus 2,500, which will give us 10,000. The square root of 10,000 gives us 100. See, the same magnitude that's here. Now, I believe that was it for section 6.3. Now comes section 6.4. This is the dot product of u. If you have vector u, right, this is component u1, comma component u2. And vector v, which is component v1 and component v2. So the dot product of u dot product v, right, you're going to multiply the first components and then add it to the product of the second components. And also for this one, I also have an observation that is real easy to use. Okay, but for now, let's do it, the way the concept is. Right, it's going to be the first component, it will be 4 times 2, plus the product of the second component, which will be 5 times 3. Then we add them, it's going to give us 23. Please remember that that the answer of the dot product will always be a number or a scalar. It will never be a vector. Okay, so a dot product will always give you the answer as a real number. Okay, again, right, this is b now, which is going to be 2 times 1 plus negative 1 times 2. So this will give us 2 minus 2, which will give us 0. Because this is important when the dot product is equal to 0, because when you get to Cal 3, you'll be doing perpendicular vectors or orthogonal vectors. You have to state if the vectors are orthogonal. And they're orthogonal if the dot product is equal to 0. Okay, so that's something to to just be aware of. Then for C part, it's going to be 0 times 4 plus 3 times negative 2, right? Then we add them. It's going to give us 0 minus 6, which will give us negative 6. This is my answer of the dot product of part C. Now here's the observation, right? They give you u dot product v. So it's going to be component u1 times component v1 plus component u2 times component v2, and then you add them. Again, here's my observation. Right here, I'm gonna prove. The proof for the for the dot product. Right. If you have this is vector u, right, which will be u1, comma u2, and the observation is put them vertically. So you're going to put the vector v1 and component v1, component v2. Now the dot product will be, right, you multiply the first components, and then you multiply the second components, and then you add them. Okay? It'll be easier when we do an example, like this one here. Right, so they give us, yeah, this is part A. Okay? Look how easy it's going to be. So again, what's the observation? I'm going to put the first component, the first vector first, which is vector u. Then I'm going to put vector v right beneath it. Then the dot product will be 8, because 4 times 2 is 8, and 5 times 3 is 15, so it'll give us 23. So a dot product of vector 4, 5 and vector 2, 3 will give us 23. Okay. Now, so these are certain properties of the dot product. Right, for example, it says here, let u, v, and w be vectors, and let c be a scalar. A scalar is any real number. So property number 1, u dot product v is equal to v dot product u, right? This is called the commutative property. If you change the order, you should get the same answer. Property number 2, which is called the distributive property. If you have vector u dot product parentheses vector v plus vector w, right, it's going to be u dot product v plus u dot product w. That's called the distributive property of vectors. Now comes a scalar. You have a scalar C, right? You're going to multiply a scalar times the dot product of vector u and v. If you notice here, you don't distribute the scalar. You only do it to one, right? For example, it can be the scalar c times vector u dot product v, or u times c dot product c vector v. That's called the associated property. Now 0 times any vector will give you 0. And also, if you have the vector v, dot product vector v, the same thing as its magnitude squared. Okay. Or if you have to find the magnitude squared, just use the dot product of vector v, dot product times itself. Okay. Example 2, using properties of the dot product. Here they give us 3 vectors. They give us vector u, which is component -1, 3. Vector v, which is component to -4, and vector w, which is component 1, -2. So here, guys, they give us parentheses u dot product v, close parentheses, times vector w. Because remember, guys, the solution or the answer for the dot product is going to give us a scalar. Okay, so let's do A part first. And here's my observation. So for part A, first I have to find the dot product of u and v. Right, there's my u, -1, 3. Right, I'm going to put the v vector right underneath it, 2, -4. Right, use the observation, so it's going to be -1 times 2 plus 3 times -4, and we add them. So it's going to give us -14. Now we bring vector w right in place, because the dot product of u dot product v gave us -14. Now -14 becomes a scalar, and I'm going to multiply the scalar times vector w. Right, there's vector w, which is 1, -2, and I'll just distribute. Will give us -14 and positive 28. So this is the solution for part A. Now comes part B. Right, here, guys, first I have to multiply the scalar 2 times vector v first. Okay, so 2 times vector v will be 2 times vector v is 2, -4, which will give us 4, -8. Now, right, so this is being down vector u, which is -1, 3. And then, because now it's going to be the product, I can just bring the vector 2 times vector v, bring it down underneath it. Right? So it's going to give us what, -4 plus -24. The answer will be -28. That's my solution. Now for C part, here, guys, this wants you to again to go over the magnitude, because the magnitude is important. So for vector C, it's something that we've done before, right? So vector u is -1, 3. So it's going to be the square root of -1 squared plus 3 squared, which will give us 10, which will be the square root of 10. So this is my solution, guys. Okay. Now let's continue. Now comes the angle between 2 vectors. So this is your formula, guys. The cosine of theta is equal to the dot product of u and v over its magnitude of u and magnitude v. This can be done in 4 steps. Okay, so really, guys, this is what we're looking for, right? The angle between 2 vectors, right? To make it simpler, cosine of theta, right? It'll be theta is equal to the arc cosine of parentheses u dot product v over the magnitude of u times the magnitude of v. Again, with an example, you can do it in 4 steps. The first step is finding the dot product. The second step, finding the magnitude of u. Third step, finding the magnitude of v. And the fourth step, put it all together. Here we go. So first, right, I need to find the dot product of u and v. It says, find the angle of theta between u, which is component 4, 3, and v, which is component 3, 5. So again, we're going to use the observation. Vector u is 4, 3. Vector v is 3, 5. Right? the dot product of u and v will be 12, right? We multiply them, 12 plus 15 will give us 27, right? So I already got the first part, which is the dot product. Now I need to find the magnitude of u. So the magnitude of u will be the square root of 4 squared plus 3 squared, which will give us 25, the square root of 25, which will give us 5. Now, step 3, I need to find the magnitude of vector v, which will be the square root of 3 squared plus 5 squared, will give us the square root of 34. Now, for the last step, right, to get the answer, we put them all together. You see the dot product was 27. The magnitude of u was 5. And the magnitude of v was the square root of 34. Put that in your calculator, guys, and you're going to get your answer. Approximately 22.17 degrees. And here's how it looks like. You see, this is vector u was 3,4, and vector v was 3,5. So they're looking for the angle between the two vectors, which is that one there. Now comes the definition of orthogonal vectors. The vectors u and v are orthogonal if and only if the dot product of u and v is equal to 0. Okay. Example, determine orthogonal vectors. Determine whether the vectors u, which is component 2, -3, and vector v, components 6, 4, are orthogonal. Right, find the dot product. So again, I'm going to use the observation. So vector u, we put it first, right? And then vector v, we put it underneath it. Now comes, right? Now comes the dot product will be 2 times 6. Here we go. 2 times 6 will give us 12. And -3 times 4 will give us -12. So the answer is 0, right? So that means these are orthogonal. Another word for orthogonal is perpendicular. Okay. So these two vectors are orthogonal or they're perpendicular. You see, and there they are. See, they're perfect perpendicular. Now comes the projection of u onto v. Here it says, let u and v be non-zero vectors such that u equals to w1, vector w1 plus vector w2. Where w1 and w2 are orthogonal and w1 is parallel or a scalar to vector v as shown in the figure below. Right? Again, right? Vector w1 and w2, right, are orthogonal or they're perpendicular. And vector w1 is parallel or a scalar of vector v, right, which is here, right? This is vector v, and vector w1 is a scalar because you multiply a certain number, right, times that vector, and it'll give you w1. So in this problem, guys, the next example, we're going to find vector w1, which is a projection of v onto u, and then we have to find w2 because if u is equal to w1 plus w2, then w2 is equal to u minus w1 because all we do is subtract w1 to both sides, and this is how we find w2, vector w2. Okay, and here's the formula for the projection. Okay, vector w1 is equal to the projection of u onto v, right, which is equal to a scalar times the vector v, okay, which is equal to the dot product of u dot product v over the magnitude squared, and then times vector v. Okay. Again, this is going to give us a scalar, and then we multiply times the vector. Okay, let's do an example. Okay, how are these examples used? For example, hey guys, like in real life, you're trying to find what force will keep this boat from going into the water. That's what we're going to be looking at. It can be a boat, or it can be a cart, or it can be a semi. It can be anything that's going downhill. See, same problem, guys. We're looking for what force is required to keep this trailer from rolling downhill. Okay. Okay, now let's first do an example of projection of v onto u, and then we do some of the word problems. Example 5. It says find the projection of u, which is a component u is 3, -5, onto v, which v is component 6, 2. Then write U as a sum of two orthogonal vectors, one of which is a projection of V onto U, which is vector W1. Okay. So what do we need here, guys? Here, guys, we need the dot product, right? We need the magnitude squared of V, and then times vector V. Okay, so let's cut it into let's see, 1, 2, and 3 steps. Right. So first we find the dot product of vector U onto vector V, which will give us 18 plus negative 10 or minus 10, right? Which will give us 8. And then I need to find the magnitude of V, which will give us the square root of 6 squared plus 2 squared, which will give us the square root of 40, right? But then when you square it, it becomes 40, right? So the bottom part is 40. So we have, right, the projection of U onto V will be 8 over 40, right? Because 8 is a dot product, and the magnitude of vector V squared is 40, right? This is the same thing as 1/5, because 8 over 40 reduces to 1/5. Now, if we multiply 1/5 times 6, will give us 6/5. If we multiply 1/5 times 2, will give us 2/5. Okay. Now, that's the answer for the first part. Now, for the second part, they want us to find, write the sum of the two orthogonal vectors, one of which is the projection of U onto V, which is W1. So we're looking for W2, right? W2 is equal to U minus W1. U is equal to 3/5, right? I mean 3, component 3, negative 5, minus the vector W1, which was 6 over 5 component, and 2 over 5, right? Right, we're gonna subtract 3, right? Component, the first component minus the first component on the vectors, and second component minus the second component. So 3 minus 6 over 5, right, will be, get this MLCD, which will be 15 over 5. This will give us a 3. Minus 6/5 will give us 9 over 5. So that will be the first component, which will be 9/5. Now we're going to do the negative 5 minus 2/5. Right, so 5 is the same thing as negative 25 over 5. That gives us negative 5. Minus 2/5 results in negative 27 over 5. So that's my solution, guys. 9/5, negative 27 over 5. That's the vector. The vector that's perpendicular to W1, which is a projection vector. Okay. Now again, the example 6. I believe this is the last one, or second to the last one. Says a 200-pound cart is on a ramp inclined at 30 degrees, as shown in Figure 630. What force is required to keep the cart from rolling down the ramp? Okay. Solution. Need to find the force vector and vector V. Right, and after that's going to give us vector W, right? W1, and then we take its magnitude to find the force. So again, this vector here, the force, guys, is equal to 0I minus 200J. The book doesn't show, the 0I. And at times, students think, well, how is this negative 200J? It's because, right, because here, guys, right, here is like the origin, right? And if it's going down, right, it's at 200 pounds, right? There's no, for the X value, it's going to be 0. That's why 0I minus 200J. And then for vector V, right, the force is just negative 200J. This is what they have in the example, but I added the 0I so students can be aware, where that's coming from. This is a force due to gravity. Now for the 30 degrees, we're going to get vector V, right? Vector V is equal to the cosine of 30 degrees I plus sine of 30 degrees J. So you have to know the components or the point of 30 degrees, which is the square root of 3 over 2, 1/2. So cosine of 30 degrees is the square root of 3 over 2, and the sine of 30 degrees is 1/2. So let's plug in those values. There they are. So this is my component form. Now, this is vector V, right? But this is in linear combination form. You see, if you notice, guys, everything that has to come with real world problems, guys, is going to be in linear combination form. right? Like in physics and also in calculus 3. Right now, I need to find, this is the formula, right? So the projection of F onto V, right? We're gonna do the dot product of F dot product V. So we have the first vector, which is a force, and we put the second vector right underneath it, and we apply the observation. That'll give us 0 plus negative 100, which will give us negative 100. So that is the numerator of the force dot product V. Now for the magnitude, right? It's going to give us, right? It's going to give us, the square root of 1, which will give us 1. If we square it, it's going to give us 1, right? That's why it's going to give us negative 100. This is negative 100 times vector V, right? We multiply the negative 100 or distribute it. It's going to give us negative 50 square root of 3 I minus 50j. So this is my vector that we're looking for. That's W1. Now for the force required, we take the magnitude of W1, right? Which will give us 100, right? So the force that's required is 100 pounds of force. That's what we find. That's how we solve these type of problems. So this cart requires 100 pounds of force to keep it from going downhill. And I believe this is it for this presentation. And I apologize for taking too long. I think it went over like 15 minutes.
No worries, Mr. Azasi. We always appreciate your thoroughness. Before I let everyone go, I would like to invite everyone for next week's session. On March 13th, we'll have some TVEs for you. The Happy Math Hour for Math 1332 will be going over arithmetic and different bases and prime numbers. And then in Math 2412, we'll be covering exam review 2. And then for the 1 p.m. TVE, it'll be counseling with Oscar Velasquez. Now, if y'all have time today at 1 o'clock, we'll have presentations from CSD and the Writing Center. Thank you all for coming in today, and we hope you have a wonderful weekend.